Welcome to Lecture 6 for Physics 4C. In this second set of lecture videos on physical optics, we continue our coverage of wave interference, going into detailed calculations that we avoided in the last lecture. First, we start with the calculation of intensity for double-slit interference pattern. This is going to be a long lecture, so it is split into a preliminary part, introducing necessary concepts and approaches. And in the second, the calculations part, we go through the whole calculation using real-valued trigonometric functions. Later on, we plan to revisit this calculation using complex exponentials. In the remainder of the lecture, we cover other phenomena that we can treat as interference between two sources of light. As we treat these phenomena, I hope you see the importance of focusing on the phase difference in the electromagnetic waves originating from the two sources. In the next lecture on physical optics, we will cover diffraction, that is, dealing with the wave interference involving infinitely many sources of light. And we will introduce some calculational tools to help us analyze diffraction.
You have enough information to sort of describe where the bright fringes are and where the darker fringes are. What I want to do right now is going a little bit beyond that, trying to describe the intensity pattern. So this is what the intensity pattern looks like, qualitatively speaking. Let me draw it the way we normally draw. So if you see a sketch of this, I don't know, on Wikipedia or whatever, you might see the intensity pattern drawn this way. Maximum here goes to minimum somewhere here, maximum again, minimum, maximum, minimum, something like this. All right. That seems good enough. Like, does this figure make intuitive sense what it's trying to describe? Yes? So it's trying to describe as a function of y. So if I'm describing an axis here, this would be the position axis, y. And what I'm trying to draw on the perpendicular axis is the intensity of light, how bright that light is. This is the central maximum, that's where it's bright. As you go off to the side, this is the first darker fringe where intensity goes to 0. And as you go out farther, you encounter bright fringe again, and dark fringe, bright fringe, and so on. Good? And so in reality, these peaks will get smaller and smaller as you go out. In the idealized version, these peaks have the same height. It's a matter of, do you have to account for single slit diffraction, which we'll cover next week. So that's how we, if we are trying to be more quantitative about what should measure, what should see, this is how we might describe the intensity that way. And so, this intensity, it could be described as a function. So let me just use letter I. We could describe this intensity as a function of position. And just the position because we are averaging it over some time because we don't really see the oscillation of electric field. Okay? So the mathematical calculation that I want to go through now is how to derive this intensity as a function of height. And you already know what kind of features you would expect. You already know whatever you get at y equals 0, you should get maximum, some kind of amplitude of this oscillation of a sort. And as you go out in either direction, it's going to go to 0. It'll never be negative. There's no such thing as negative intensity. And it'll get maximum again. So it's going to be something sinusoidal, but modified version of something sinusoidal. Okay? And so before we go headlong into the whole calculation, let me just step you through a couple simplifying conventions. So is everyone here familiar with the definition of intensity in physics? I think even I may not have covered that. I probably didn't cover it in Physics 4B. So let me define the word intensity, because it's very possible that we haven't defined it. So intensity in physics, you can talk about intensity of light. You can actually talk about intensity of other things as well. Intensity is defined as this: power per area. Okay? Everyone remembers how power is defined? How is power defined? Daniel. Work over time? Yeah, so work gives you change in energy, right? So you can talk about work. I want to be a little bit more general. So power would be work, or I want to talk about change in energy. Change in energy per time, or some kind of energy per time. That's the mechanical description of power. And hopefully energy, you have some sense of what that is. So this laser pointer, it has a power of, I don't know, I can't read. Okay, it says max output power less than 5 milliwatt. So it has a power of 5 milliwatt, let's say, if it's a maximum. So that's the power that's in this entire light beam. But depending on where you are looking at this light beam, the size of the light beam actually changes. Near my hand, it's probably, I don't know, diameter 5 millimeters. Seems a little bit big, 3 millimeters. But as you go farther away, even though this is a well-collimated laser beam, if you go far enough away, it gets bigger. So if you go 100 meters away, this might be 3 centimeters. So this has a fixed power, but its intensity changes because as you go farther away, the same amount of power is being spread over a larger area. Okay? So when we are trying to describe intensity, this is what we are trying to describe. That so let me give you some complicating factors you have to consider. Let's say you have, I don't know, some light bulb. Let's say you know what it is. It's a 60-watt light bulb. What would be its power? Including all the spectrum of light, both visible and invisible.
60.
About 60 watt, right? Yeah, visible is a fraction of that, but including everything, about 60 watt. Now, suppose if somebody asked you for intensity of this light bulb at some distance, I don't know, 1 meter away. Somebody asked you for, so there's a light coming from this light bulb that's shining everywhere, and someone asks you, what is the intensity at some distance 1 meter away? Do you know how you might estimate or calculate that? You could. I want to do it with only the information that's on this board. Imagine that I have forgotten all about Maxwell's equations. I don't remember any of it.
The area of this piece over 4 pi multiply 60.
All right, so let me start the other way. Multiply by 60 watt. What else did you say?
The area of this piece
Okay.
divided by 4 pi. That's
Uh-huh.
a whole circle.
Yeah, you are going somewhere close. So this is close, but not quite. Let me give you a simpler way of thinking about this. Intensity 1 meter away at this spot. Intensity 1 meter away, I don't know, over here. Do you think they would be at same intensity? Yeah, in general, right? Let's say this light bulb is omnidirectional. It's not like this laser beam, highly directional. It goes in all directions. So if you make this simplifying assumption that intensity all around is the same, it makes it a little bit easier to calculate the intensity, because you would use the total power. And what area would you use? Area of the whole sphere enclosing it, yeah. So for intensity here, this is how I can estimate it quickly. I can say, well, it should be the total power, 60 watt, divided by the area, so that's the sphere. So 4 pi times the distance squared. 4 pi times 1 meter squared. So that would be the intensity. It would be a function of distance. As you go farther away, it would fall off at distance squared, and hopefully all of this makes intuitive sense mechanically, right? All right, so this is one consideration I want you to just have in the back of your head. And all of this is consistent with the conservation of energy and all that good stuff that hopefully you seems familiar to you. Now, let me tell you what an experimental setup for double-slit interference might be like. So for a double-slit interference, it might be like this. You could have a single slit. This is the picture you saw over there, which lets in some light through. So there's light that's diffracted through this single slit that we'll talk about on Thursday, starting on Thursday. And then we have a double slit. So some fraction of this light that's reaching this double slit screen would go through here. Good. Some would go through here. Let's say you knew the intensity of light at this point. You know intensity I naught. And let me make this simple for now. Let's just say I'm going to block off the other slit. So for the time being, you don't have to worry about this second slit here. All you are worried about is the first slit, slit number 1. And on this screen, let's say I'm looking at what is intensity as some function of y due to slit number 1 alone. Let me ask you this question. If you were given this, if you're just given this information, let me give you a little bit more information. Let's say you know the light source, you know the distance 0, you know the distance 1, and you know the final screen distance. Do you feel like you have complete set of information in determining intensity here as what fraction of intensity here? Yeah, I'm hoping you feel this is an underdetermined problem because you'd have to know what the size of the slit is here, here. There's a bunch of more information that you should feel like you need to know. So I want you to start from there. But let's say I ask you this question. I simply want to, all I want to do is, let's say I have I naught, and given this I naught, I know this function. And I'm now going to just describe the changes to it. Let's say I double the intensity here. How do you think this intensity should change? Double. Whatever it was, it would now be double, right? So we can deal in proportionalities. We can deal with this light intensity here being proportional to some original light intensity. So this is the language I want to use. So I actually want to get rid of all these because they're not adding anything new. So I just want to talk about slits 1 and 2. So I have slits 1 and 2. And I have some intensity of light here that would be due to slit 1 alone, and some intensity of light here that would be due to slit number 2 alone. And in fact, let me put it this way, that let's say the intensity of light, let's say the I naught is intensity of light due to either slit alone. Intensity of light at the screen. So this is a simplifying convention I'm introducing. If we are doing the other thing, where I give you the magnitude of electric field here, I mean, there is some amplitude of electric field here, E naught. And But if I'm starting from that and ask you to calculate the intensity here, there's a bunch of things you're going to need to take into account. So to make our calculation simpler, what we are going to say is that we can kind of measure what the intensity would be if there was only one slit. And if there is only one slit, the pattern of intensity, at least approximately, what it should look like is it should, it should sort of peak out in the center and then kind of get, smaller as you go farther away. And if this slit is narrow enough, this is going to spread out so much that your intensity. So this is the sort of baseline intensity. This intensity I naught is this intensity. That's what intensity you would have with a single slit and nothing else. Good? Now, if I add the second slit, what do you think will happen to the intensity here? I mean, you know the general features, right? You're going to start to seeing interference pattern. You are going to see places where the intensity actually goes to 0. So let me just mark those places so that we are going to talk about that later. So there are going to be some places where you get destructive interference with two slits. So their intensity will be 0. We'll work that out. Now, how do you think your maximum intensity will change? I'm asking everyone. Do you think it'll double? I mean, it'll be greater than intensity for the maximum intensity. It'll be greater than intensity with a single slit, right? So how much greater? Greater by a factor of 2 or some other factor? 2 is an easy guess. So how do you think? So let's just explore that a little bit because 2 is a common guess. And that's the guess that makes sense to a lot of people because that reminds you of what I did last time. If you have a baseball, tennis ball. If you have a tennis ball, constructive interference is like adding a second tennis ball, so you have 2 tennis balls. Truth is, that's a simplistic description that's kind of wrong. So let's say your initial guess was this. You have, so let's say this is the place where it's a 2 I naught. And then pattern that you are imagining would look something like this, right? Let me tell you in 2 ways how you can guess that this pattern that we are drawing is actually not quite right. So you have to imagine, tilting your head and looking at this graph. When you average I naught over this space, it's just I naught, right? It's a constant function. When you average this double slit pattern, what does average roughly look like? Again, I naught. Now, is that what you would have expected? You have some total amount of energy going through one slit. When you have second slit open, how much total energy do you expect going through both the slits together? Double the energy, right? Double the energy, that's the intuitive thing. Energy is conserved. So that's what you should expect. When you have 2 slits open, so there's double the amount of light waves coming in, you should have double the total amount of energy here. And with this 2 I naught, that doesn't work. So what should this value be so that the total energy is conserved? 4 I naught. It's not intuitive. So with the 4 I naught, it would look like this. I don't know. This picture doesn't really mean anything. But when you have this, now this is a pattern that will average down to 2 I naught when you average it over space. And that would be double the total power going through one slit. And that agrees with our intuition about energy conservation and all that. Let me give you the second way of seeing why this maximum intensity, so max intensity, should be 4 I naught instead of 2 I naught. You might have noticed my switch over in language from the first hour of today in the second hour. Here, I was talking about electric field. At some point, I switched it over to intensity. Electric field is not the same thing as intensity. Can intensity be negative? No, I mean, there's no such thing as energy, negative kinetic energy. Can electric field be negative? Yeah, if one direction is positive, then the other direction is negative. So, I mean, you can say it here, this can be negative. So electric field can be negative. Intensity is not. And I guess this is the relationship I have to give you. If we had more time in Physics 4b, we would have covered this in Physics 4b. We didn't. You can look at it in the textbook. There's a relationship between the intensity and electric field. And I will just write down this much. Intensity of light is proportional to electric field squared. So by using this language of proportional to, I'm hiding a bunch of numerical constant factors that I frankly don't remember. But what is important is the way you get intensity is by squaring the electric field. And this relationship is actually pretty robust. You can, this can be intensity as a function of time. And that would be the electric field as a function of time squared. Not that it matters because we end up averaging over anyway. But that's actually important because if you average this over time, what do you get when you average electric field over time? You get 0, but that doesn't mean 0 intensity. Because when you look for average intensity, you first square this before you do any kind of averaging. Yeah? So this is one relationship that will help you understand this. So we talked about superposition principle, right? Superposition principle, it holds for electric field. It holds for what we were talking about in the first hour of class. It does not hold for intensity. I mean, imagine this. Intensity due to one slit is this flat line. Intensity due to the other slit is another flat line. If there was a superposition principle for intensity, your total intensity would be simply this flat line shifted over. But that's not the case. It doesn't hold. And this is really the reason why it doesn't hold. It's because of this square. The electric fields obeys linearity property. Intensity doesn't, because you are squaring things. So on this screen, what you want to describe is the, so if you were trying to say what the total intensity is, and if you were trying to say that intensity due to one slit plus intensity due to the other slit, that would be wrong. That's not right. Instead, what you can do is you can say the total electric field is equal to electric field due to one slit number 1, as a function of, I guess, position and time, plus electric field due to slit number 2. Once again, as a function of position and time. So this is true. That's the superposition principle. And so what do you do when you want to get the total intensity? Yeah, you take this and you square it, and the total intensity is at least proportional to that. So let me just write that out quickly so that you can kind of see where all this comes from. So the total intensity would be proportional to the total electric field squared, or let me just write that out. It's this whole thing squared. So I'm going to get 3 terms: E1 squared plus E2 squared. And I actually recognize these first 2 terms. These 2 terms I can recognize as this is what leads to intensity due to one slit number 1, right? So it's actually going to be a constant value. This is what leads to intensity due to slit number 2. So that's also going to lead to constant value. Both of these are equal to, each individual equal to I naught. So if all you had was this, then you would have 2 I naught, constant value. But it's not that, because you have the cross terms. You have E1 times E2 plus E2 times E1. Or you have this, plus 2 times E1 as a function of position and time times E2 as a function of position and time. And this is the interference term. This is what leads to that interesting pattern of intensity. At some places, this will be as large as plus 2I naught. That's where you get 4I naught. In some other places, this will be as small as minus 2I naught. So this leads to a range of values from minus 2I naught to plus 2I naught. So this is where you get destructive interference. This is where you get constructive interference. So the rest of the method that I want to go over is working out this math. So the rest of the method that I want to go over is working out this math. So I've already done a quarter of it. I have these two constant terms. So I can say my intensity total is, so the intensity pattern, intensity total is equal to 2I naught plus, and I have to work this term out. Good. So I guess let's do that. Plus dot, dot, dot. Let me leave this as a blank, which we'll have to work out. Good. All right, so I guess let me set up some things to start talking about it. Let's see, what's the good place to go? So let me call this calculation of E1, E2. And I want to be careful here because there are some simplifications I will need to make that kind of mirrors what we were discussing earlier qualitatively with the locations of bright fringes and dark fringes. So the first thing I want to do is, this is written in terms of just y and t, and I can already tell you that that's going to look complicated. So I don't really want to deal with that. Let me write out this much. So because I'm going to be making some approximations, I want to make sure each step is clear and at least you know where I'm waving my hand. So when I have E1 yt, well, it's going to be some amplitude of oscillation E naught times, and function of y, that's the complicated piece that I don't really want to deal with. And let me backtrack to this portion. So electric field on the screen, it's going to be something that oscillates as a function of time, right? So it's going to be some amplitude times cosine of omega t, right? But just this, it's way too simple. I mean, where is the position dependence, right? So the way I want to include this position dependence is this way. I want to include it as a phase factor, omega t plus the phase due to slit 1, which is a function of y position. Is this expression clear? Does that seem reasonable? Yes? So this way I can describe the electric field on the screen as a function of y position, which would be expressed as this phase factor here. And this also matches with what we were talking about for effect of a single slit, because that phase factor would go away. Sorry, I need to move on. So let me do it this way for slit number 1, and do it the exact same way for slit number 2. So it'll be E naught times cosine of same frequency, and then it'll be plus a different phase factor. And it's because those two slits are slightly separated, how much the phase changes will be different. So it's plus V2y. Good. I think this is a good starting place. And I guess, yeah, I think I can actually take this from here. So what I'm going to do is I'm going to literally calculate this product here. Yeah? And it's going to be simple enough. So it'll be, well, so let me do it in purple, different color. So E1 times E2 will be, well, E naught times E naught, so E naught squared. So this E naught squared term is what's going to give me that, the I naught, right? All right, I have that, times, I'm skipping a factor of 2 here for now. So, yeah, so E naught squared times, and this is what I have, cosine of omega t plus phi1. I'm just going to remind myself that phi1 is a function of y. It's not a constant, in case that matters later, times cosine of omega t plus phi2. Once again, function of y. And later on, what I will imagine doing is I'm going to imagine taking an average over this over some time. So this is the place. So when I take an average of this over some time, this is what you can imagine. You can imagine that I'm integrating this as a function of time t from some 0 to some, I guess, period. One period t divided by 1 over t. That's the time average. So this is constant. I can pull it out. Anybody here know what the time average of this is? I want you to be careful. These two angles are not the same. If you're thinking of time average of cosine of x squared, this is not. We have to do more math. So what I need to do as an intermediate step is I have to expand this out, see where that takes us. I haven't done this before class because of the chair's meeting, and we'll see where that goes. Okay? So let me expand it out. Everyone here remembers the angle addition formula by now? Yes? Okay, then I can just write it out. So, so let me just do this portion. So this portion here that I'm going to write out is equal to cosine of omega t. So should I, you know what, I need to write it out for my own purposes. So let me do that. So the angle addition formula, I only need a cosine one. So cosine of alpha plus minus beta is equal to cosine of alpha, cosine of beta, minus plus sine of alpha, sine of beta. So that's the trig identity that I'm using, that hopefully everyone by now remembers. And so cosine of omega t times cosine of phi1 minus sine of omega t, sine of phi2. I'm sorry, not phi2, phi1 still. All right, that's my first term times the second term, cosine of omega t times cosine of phi2 minus sine of omega t times sine of phi2. Good? Didn't make any mistake? I need to expand this out. There are going to be 4 terms from each one of the multiplications. So this one first. So I will get cosine squared omega t, cosine squared omega t times cosine phi1 and cosine phi2. So cosine phi1, cosine phi2. All right, 1 term down, second term. Second term would be, let me do the same thing except with this one. So cosine omega t times sine omega t. So minus sine omega t cosine omega t times sine phi 2 cosine phi 1. Sine phi 2 cosine phi 1. Everyone following so far? I'm down two more terms to go. So the second term and these two. So it will be minus sine omega t cosine omega t. Sine phi 1 cosine phi 2. Let's keep going. Oh, that's it. Second term, the fourth and the last term is minus, so plus, minus times minus, so it's plus. So this term here, sine omega t, sine omega t, sine omega t squared times sine phi 1 times sine phi 2. All right. Do people see simplifications that I see? That's making me smile a little bit, because I think it's getting a little bit simpler than I thought. I can combine two wait, can I? No, sorry, I misspoke. Sorry, I don't see the simplifications. I have to do the time average. So this is the part that I'm not going to write out, so I want you to follow carefully. So it's a place where I want to use your knowledge that you're about to develop about the time average. Time average of this, and time average of this over one cycle. So in other words, I want to quickly derive these three formulas. Cosine squared omega t dt going from 0 to 1 period would be 2 pi over omega. Is that right? Yeah. And let me make this simple for myself. I'm going to just say some arbitrary unit time t, and this will go from 0 to 2 pi. Yeah, and I guess I have to divide by 1 over 2 pi. Yeah. So what this is equal to, and the same thing for the other two. So going from 0 to 2 pi, 1 over 2 pi, sine squared t dt is equal to something. And the very last formula, 0 to 2 pi, 1 over 2 pi, sine of t times cosine of t dt is equal to something. I guess depending on how well you did in calculus, you might recognize this. You kind of see this often. Does anyone remember the first one? Should be 1/2. This is the trig identity you use. You use power reducing formula that says this is, So this should power reducing formula should be 1 plus cosine of 2t over 2. Right? Yeah. So go through the calculation, you get 1/2, because this integrated over 2 full periods will give you 0. Okay? Similar thing for this. This should be 1 minus cosine of 2t over 2. So you actually get 1/2 here as well. Good? Okay, yeah. I have other points I want to make, so I want to go through this quickly. What about the last one? Yeah, you use double angle formula. So when you simplify this, you'll get sine of 2t divided by 2. So what's this integrated over, I guess, 2 full period? 0, right? Yeah. So this will give you 0. So we are going to use the fact that these three terms, these three types of expressions simplify to something simple when you average it over the time. So when you do this time average, This is the only thing that's going to remain. This term multiplied by 1/2. This term will go away entirely because sine omega t, cosine omega t, when you do the integral, it'll go away. Same thing here. Sine of, this will go away when you do the time integral. So this is 0. And this term will also remain with the factor of 1/2. So when you imagine doing all this calculation, which we frankly haven't, but let me just write out the result. The result will be this, that this complicated expression simplifies to E naught squared. This is after you have done the time average. So by now you should have nothing depending on time. You have E naught squared divided by 2 times divide by 2. I feel like I missed something. Yeah, let's keep going. Cosine of phi1, cosine of phi2, plus sine of phi1 times sine of phi2. Can you simplify this further? You put through this in reverse, right? Yeah. So this simplifies to E naught squared over 2 times, I feel like I missed something. It becomes cosine of phi 1 minus phi 2. So when you put this back in here, I'm off by a factor of 2 somewhere. I'm not sure where. Where am I off by a factor of 2? Oh, I know where. Let's see. I know where I'm off by a factor of 2. I just want to introduce it at the correct place. Okay, I think this is where I can introduce it so that it won't seem like I'm just making stuff up. So we've been talking about how this I naught is coming from E naught squared, right? Yes. But we didn't spell out exactly why. But I want you to see that if we have this E naught squared as a square of E naught times cosine of omega t, that we are first going to square and then take this time average thing that we are doing over there. What you will end up here on this side before you make this jump is actually E naught squared over 2. Good? Because you have cosine squared omega t term still. So when you do the time average, you get 1/2. So wherever we see E naught squared over 2, that's what we would associate with I naught in intensity. Good? So now that I have this expression, this is what I can say. We started out with this, right? Started out with E1 times E2, leading to this expression. And when we make the jump here, from here to an expression for intensity, I'm going to say this E naught squared over 2 is equivalent to intensity from a single slit. So this would become I naught. I naught times, the rest would be this, cosine of phi 1 minus phi 2. Good? Okay, so let me write that out. So here we have then, for this total intensity, I got these 2 already, 2 I naught. I have this 2, so let me write that in, plus 2 times, and I have this E1 times E2, which we did here, and then took the time average, and resulting in this, I naught times cosine of, instead of phi1 minus phi2, let me write it down this way. delta phi, phase difference. Right? It's the difference in phase from the electric field coming from those two slits. Yes? And we already have a way to get this phase difference from any other information given in a problem. Like that's what we were working on before, right? If you have this geometry to figure out this delta x, then the phase difference delta phi. So we never really figure out individual phase due to one slit or phase due to the other slit because that's going to get complicated, and we don't need it. All we need is the phase difference, which will be 2 pi times path length difference divided by the path lambda divided by the wavelength. Yep. So this is the big expression for intensity. It does take a fair amount of calculation, but the end result you see is actually pretty simple, and you will be able to see that this is actually correct. We can do a little spot check. At the central maximum, what is delta phi? 0, right? So this is cosine of 0 is 1. So I have 2I0 plus 2I0, giving me the maximum intensity of 4I0 at the central maximum. Yeah? And as you increase in y, this oscillation in space you see, that looks like a cosine oscillation, right? And I can show you with a small angle approximation that this portion does look like a cosine of y. Because with a small angle approximation, this is what you can say. So taking these two expressions here, this is what it would look like. Delta phi is equal to 2 pi over lambda times d sine theta. And with a small angle approximation, this theta just becomes, sine theta becomes theta. And in fact, and you can express theta, which is arctangent of y over L, as approximately just y over L under small angle approximation. So this theta would be simply y over L. So that's the approximate expression for phase difference for sort of small physical angle of deviation from the central maximum. So, so you have this complicated constant, 2 pi d over L, but the dependence on y is this. And when this delta phi goes in here, it'll look like cosine of 2 pi over lambda d over L times y. So it does go as cosine of y. Okay? Yeah, so that's what you see here. As you change in position y, you see something that varies as cosine, and that's what we get in our derivation. It's I guess in the end, it's the end result is simple. Which we should have expected, because when you just plot it out based on our intuition, it's something simple. Right? Okay, any questions, comments? All right. So let me start out with the thin film interference, because that's, I think, the one where I could give you a lot of calculation questions, because we haven't quite covered the important concepts, I couldn't give you problems yet. So as we are going through these topics, I want you to keep one thing in mind, is what we have been covering since day one of when we are doing physical optics. So for interference conditions, for constructive interference, you need whenever you are looking at interference, you are looking at phase difference. That's why it's important that two light sources are coherent. So you are looking at phase difference for constructive interference of multiple integer multiples of 2 pi. So 2 pi n, where n goes from 0, 1, 2, and so on. And for destructive interference, you are looking for an odd multiple of pi. So your phase difference goes from, how should I write this? 2n plus 1 pi, where n goes from 0, 1, 2, 3. Good? This sounds familiar? I think everyone remembers this. The reason I'm bringing it up again and having it written here is as we analyze these situations, so some people have this approach. You want to memorize formulas. So for double slit, you want you to memorize some formulas. For single slit diffraction, you want you to memorize some formulas. And I'm telling you that it's going to be so much easier if you focus on the phase difference. And everything you do for all these different arrangements is just trying to figure out what the phase difference is and use that to figure out is it constructive or destructive interference. So this will be especially true for thin film interference because there isn't really a single formula I can give because as you change some situations, it'll change the conditions and whatever if I'm trying to give you a formula, whatever formula I give you will just branch out into multiple different ones, and it'll be so easy to get confused. So I want you to focus on this. Our goal is to figure out the phase difference, and for a given situation, we are simply going to try to analyze it to see. So analyze to see if we are trying to get destructive interference, then what do we need to get this phase difference? So let me cover this with some examples. So all of this is covered under what's called the thin film interference. And if you want a diagram, well, maybe you don't. I want a diagram. There's a good diagram of thin film interference in your textbook, 3.4. And this is the picture I want you to have in mind. And let me actually simplify some things in this picture so that you don't have to worry about some things unnecessarily. For the kind of situations we are going to look at, we are always going to say this. We are always going to say that these angles, whatever they are, we are going to say they are very close to normal, so these angles are more or less approximately 0. Maybe that's not always the case. We are just going to make that approximation to make our calculations easier. So you won't have to worry about the geometry, all the refraction stuff. Yeah? So that's one simplification, and I guess that's it. And so when you are looking at thin film interference, what you are seeing is you are seeing two beams. One beam is that one that reflects off of one reflective surface and comes to you. This is the beam 1. And the second beam, it comes along the same path, but you are considering one that refracted through the first reflective surface, and then it reflects off the second reflective surface. And we are assuming that by the time you look at it, these two are close enough in space that they overlap and they're going to interfere with each other. And so when you look at these two beams, where does the phase difference occur? So this is the key question. Where does the phase difference, delta phi, occur? Is there any difference in phase before either of these two beams start interacting with this first layer? No, right? It's common for both of them. So on this reflection is one place where you might get some phase difference. So you might have something happening here. One beam reflects, another second beam refracts. And there's a phase difference going on within this layer, right? So the first beam never went into this layer. The second beam went through the layer and then comes out here. So there's whatever happens in between here that's going to lead to some phase difference, potentially including this reflection here. Okay, let me finish tracing the steps to the end. What about after this second beam comes out here? So from this point to the end. Any phase difference? No, they are going through essentially the same path. This is where it's useful to assume that the angle is 0. Then you can say, these are just parallel rays, no path length difference between them. So with this thin film interference, you are going to focus on what's happening with this layer. What happens on reflections and what happens as the beams pass through. So let me work out 3 examples. These are sort of typical physical situations where you see this happening. So the first would be thin film of oil on water. Have you seen, on a rainy day, which I guess, did it rain yesterday? I thought it rained recently.
Yeah, it's
A little bit, yeah. So on a rainy day, you sometimes see this on the road. When a car where there's a little drop of oil, you see rainbow colors on that oil, right? And that's a result of interference that's going on with a thin film of oil on top of water. So we'll analyze a situation like that. And the other one is thin air gap between glass plates. Let me call it glass slides. And finally, the last one is Newton's rings. Let me actually number this. So examples 1, 2, and 3. And actually, let me pass out the demo for example 2. It's this diffraction grading that you have seen in lab. But what I want you to look at as I pass this around is I don't want you to look at it as diffraction grading. I want you to look at the kind of gap between the protective glass cover and the thing behind it. So take one and pass the other. Ignore the fingerprints because some people are, guess one per table, please. Let's see, one per table, please. So what I want you to take a look at here is, as you look at this, if you look at it from some angle, trying to reflect the ceiling light here, then you will see some pattern, sometimes rings, a little bit of rainbow colors or pattern. So that's a result of interference. You are, depending on the exact thickness between the glass plates, you are either getting destructive interference for certain colors. So if you get destructive interference for blue, it will maybe appear a bit reddish. So that's where those rainbow colors are coming from. So let's just analyze these examples, and I will introduce some new rules that you have to know as we are going through this example. And these rules will relate to how we handle each one of these points as the interaction happens. Let me number them. A, B, and C. Yeah, I guess that's good enough. All right, so let me do the first example. Thin film of oil on water. So you have, I say thin, but I'm gonna draw it big so that I can actually draw it. So example 1. So thin film of oil on water. And this is the typical way a question might be worded. Like on your homework question maybe, that I'm gonna assign soon. A question might say, so you have some oil slick, and as you are looking at it from above, you see that there's a destructive interference happening for particular wavelength. So let's say, or constructive interference for particular wavelength. So let me word it this way. So use part A and B. For part A, let me say, as you are looking at it from above, you see bright fringes for green color, let's say wavelength of about 500 nanometers. And the question could be, what is minimum thickness of oil? Yeah. And part B could be, let's say, you see destructive interference. Destructive interference for, let's say, blue wavelength. So maybe as you're looking at it, you see reddish color, so you assume blue wavelengths are getting canceled out. So wavelength of about 450 nanometers. Same question, what is the minimum thickness? Question seems clear enough, right? It's well defined. Yes? Clear enough? Okay. So let me just go through analysis of this, and we will introduce any new rules that we need to use as we are going through it. But all of those new rules that I'm going to introduce, it'll relate to the phase of the light that you're looking at. Some rules, it'll be easy to understand. Some other rules, for this lower division class, I just have to give it to you, and you just have to trust me. Because it's something that's derived in upper division, and I don't know how, well, no time, and I don't have time to drive it in this class. And I probably take a while to figure it out too. Anyway, so you have some light coming in. Let me just do it. Oh, let me actually do it in green. Since that's the neutral color. So you are imagining this situation, layers of air, oil, water. You have some light coming in. There's some reflecting from the top. Let me call this beam 1. And it refracts through. There's some reflecting from the bottom. And let me call this beam 2. These two beams are interfering. That's what's leading to these patterns that are being described, similar to what you saw with the glass plate. So, I guess this is what I'm going to do. I'm going to say that there's some reference phase that I'm going to say that's a zero phase. And so because, if you are looking at the phase of light arriving here, it's going to be constantly changing as it oscillates. So what I'm going to do is, there's some sort of neutral zero reference phase. That's what it would be if I had a beam that came in, went here, just turned around, came back. That's my reference phase 0. And I'm just going to account for any phase changes from that. Yeah? So let me account for phase changes for beam 2. That's a little bit easier. And then we'll get to phase change for beam 1. Yeah. So I guess it's a little bit underspecified. Let me specify the thickness of this oil slick, because that's what the question is asking for in the end. What is the minimum thickness? So it has some thickness t, lowercase t. And what is the source of the phase difference? Phase change to beam 2. Like, what do you see happening to this beam 2 that's going to lead to phase change?
Difference of the path length.
Yeah, it's traveling this extra distance, right? So let me start from what I might write down. So you might say, okay, it's traveling this additional distance of 2t, twice the thickness. So you just say twice the thickness divided by the wavelength of light, lambda. And if you went ahead with this calculation, you will find that you get wrong answer. Whatever answer you get doesn't quite match what the correct answer is. So what am I forgetting here?
The phase change due to the reflection.
It turns out when we introduce all the rules, I'm going to set up the situation so that there is no phase change here. That's why it was easier to do it with a beam 2. Something is wrong with this lambda that I'm going to plug in, because I'm going to plug in lambda of 500 nanometers, and that's not quite right.
Does it change?
Why does it change?
Because the speed of light slows down.
Yeah, speed of light changes. So what you need is you need an index of refraction. So let me specify that index of refraction. For oil, you can give a range of numbers. So read the problem carefully whenever you get it. For this problem, I'm going to say n is equal to 1.5. It's a reasonable value for index of refraction of oil. I'll just say that's what it is. So index of refraction of water, as a reminder, is 1.33. So NO and water. So let me just try to guess the formula. With this index of refraction, does the wavelength increase by this factor or decrease by this factor? Decrease, right? The frequency is the same, but the speed is slowing down by this factor, so the wavelength gets shorter by that factor. So it would be, so I don't know, lambda divided by NO. Okay? All right, so I think that's correct as it stands. When you use this for the amount of phase shift that happens to beam 2, that'll be correct. So you have to account for this change of wavelength, and that's what I'm labeling here as B. So you have to account for that here. That's my B here. So all right, so that's done. And when you first look at this and you haven't been told the new rules that I'm going to tell you, it's easy to think of it as, well, nothing really happens to beam 1, comes down here, turns around, goes that way. It's easy to think of it as phase shift to beam 1 is equal to 0 and end up with total change of phase, phi2 minus phi1 is equal to 2t over lambda over NO. It's easy to do that, and what I'll tell you now is when you do that, you'll get the wrong answer. Whatever answer you get won't match up with what you are supposed to get. So this is where I have to tell you the new rule. This is a rule involving phase shift. So whenever you have reflection going on, reflection from N1 to N2, or reflection from N2 to N3, you have to check for a condition. And depending on what that condition is, you are going to either get a phase shift or you're going to not get a phase shift. So let me label it here. Let me set them in this order that sort of matches up there. So let's say N2 is greater than N1. This is 1, this is 1.5, this is greater than that. And the way I have it set up there, N3 is smaller than N2, right? 1.33 is smaller than. So here you have two different types of reflections here. Here you have reflection from smaller index of refraction to larger index of refraction. Here you have reflection from larger to smaller index of refraction. Then what I am telling you, this is a new rule that you just have to memorize without any real justification. Here you get a phase shift of pi. You can think of it as if there's a little pulse coming in, as it reflects here, the pulse flips over. You might have seen that on a wave on a string, right? And here, you have no phase shift. Here, phase shift is 0. Imagine a pulse coming in. When you reflect from here, the pulse goes out in the same way it was. You might also remember seeing that from a wave on a string. Yeah? So, yes?
Is it only are these conditions where if N2 is greater than N3, the phase shift 0?
Yeah, and these cover sort of all the cases where reflections happen. Because if they're the same, then you won't get any reflection, right? So that's what you have to compare. You have to compare the index of refraction, and if the index of refraction increases, then you have to make sure you include this phase shift. Yeah. So that's what we have to account for here. We have to say instead of 0 degree phase shift, compared to some reference phase, phi1, the beam 1, actually does have a phase shift. that doesn't depend on thickness, doesn't depend on other things, but there is going to be a pi phase shift for beam 1. So when you do phi2 minus phi1, there will be minus pi. Good? So that's the correct expression for phase shift or phase difference between the two beams that accounts for all the things that you knew about but maybe wasn't paying attention to quite yet. And the new things that, so I guess this is what I'm going to label as A. New things that you didn't know before, frankly. Somebody had to tell you this. In an upper division electrodynamics, you can actually derive this phase shift, but this is not upper division electrodynamics. So yeah, that's the relationship for phase shift. Then the rest of what you do is a matter of looking at the interference conditions. And since I'm looking for constructive interference, I would say the phase difference is going to be integer multiple of 2 pi. So say that this difference is equal to 2 pi n. And what I like to do is I prefer not to plug in a particular value of n until I have an expression for thickness. Once I have an expression for thickness, then I can figure out, okay, what value of n gives me the minimum thickness. Yes?
Should the phi2 have a factor 2 pi? 2 pi multiply 2t over lambda?
Oh, you're right. So this is in the units of cycles. So yeah, is that clear to everyone? Why this needs 2 pi? So this 2t over wavelength, it's giving you the phase shift in the units of fraction of a cycle. So if twice the thickness is exactly the wavelength, then it would have been 1. But in unit of radians, what I need is 2 pi, not 1. So what I need here is the whole thing times 2 pi. Yeah, thank you. Yeah, I kind of missed that. So there should be a factor of 2 pi times all of this. Good. Okay, so let me cancel out the pi's because I think I can do without some of these pi's. So cancel out this pi. Guess I'm going to solve for t. So I have minus 1, which I'm going to move over. So 2n plus 1. Let me solve for this first. So I have 2t over lambda over no is equal to 2n plus 1 divided by 2. Everyone good so far? Okay, and I need to solve for t, so multiply through by lambda over 2no. So multiply through by lambda over 2no. That would give me t. This will cancel out. Good? Okay, so what value of n do I want if I want minimum thickness? 0, right? Yeah, so that would be where this thickness is just enough so that this pi phase shift is exactly balanced out by this phase shift due to the additional length here. Yeah. So I put in, looking at this, I put in the n equal to 0 and plug in the rest of the numbers. Since I've been starting out with the numbers, let's just plug in and see. So with this 0, it's 1/2. So 1/4. It's 1/4 times the wavelength in air, 500 nanometers, divided by 1.5 or 3/2. 3/2. So it's 1/2 times 3, so 1/6. 500 divided by 6 would give me around 83 nanometers or so. Good? Yeah, so that's the answer. So the minimum thickness that would give a bright fringe for green light, it's a pretty thin thickness. I guess. Anyone here know about CPU manufacture processes? There used to be something called like 70 nanometer process. It's smaller now, right? Do you know how small?
45.
45? Okay, so in semiconductor manufacturing, that's how small they are making things when they make, your computer chips. So anyways, that's the minimum thickness. Since we have almost everything set up, let me do part B also. And here you will actually have to be a little bit careful. It's a matter of your interpretation of questions. So let me set up what we have to do. So I'm going to erase this so that I can reuse what we had here and take it from there. So let me erase all of this. So have 2 pi back, 2 pi back. So, wait. So it's this right-hand side that's going to change. So the expression for phase difference hasn't changed at all. What has changed is what we are looking for. Before, we are looking for constructive interference. Now we are looking for destructive interference. So we say, all right, so this is equal to 2n plus 1 times pi. As before, the pi factors cancel out. So let me do the same solution as last time. Divide it through by, or move this 1 over, divide this through by 2. So what I will have is 2t over lambda and O is equal to 2n plus 1 plus 1 plus 2 divided by 2, or n plus 1. And your limitation on n is that it has to be integer. Sorry, I started at 0, 1, 2, but it's 0 plus minus 1 plus minus 2 and so on. So what value of n do you want for minimum thickness?
-1.
Now, -1 is an easy answer to give. So this is where I want you to be a little bit careful. It sort of depends on the exact reading of the question. If you want to be super legalistic and literal, you do want the literal minimum thickness. That would give you a destructive interference for this. But it's a question of how do you know that there's a destructive interference for this wavelength? Is it because you see no light of that color? Or is it because you notice the other color more? Because let me ask you a different question. If n is equal to -1, does it matter what wavelength you have on whether that you are going to get destructive interference or not? Like you would get destructive interference for all wavelengths, right? And it makes a conceptual sense here too. So if this thickness is very, very thin, so the beam 2 is not getting any more phase difference, then they start out at pi phase shift apart. So if it's very thin, then with the fact that you do get destructive interference doesn't depend on wavelength. So that would be the situation where you look at a very thin film of oil and you see no light reflecting back, because all wavelengths of light is getting canceled out. Yeah. So if that's what you're looking for, then sure, n is equal to -1, and your t is equal to 0. So now, if that's not the answer you are looking for, then that's where you have to reason, okay, we do want destructive interference for this, but we want for the other wavelengths, we don't want destructive interference. That's where you might make a judgment call and say, oh, n is probably 0. So it's the next thickness. Instead of t equals 0, I actually want t equals something else. So that's the kind of reasoning that you might go through. And when you're done, the end result is that you are plugging in 0 for this. So all of this is equal to 1. So when you solve it for t, this is what you end up with. T is equal to lambda over 2 NO. Lambda over 2 NO. Oh, so that's the same wavelength I had except double that. So it should be something like 167 nanometer or so. Good. So, wait, sorry, different wavelength. I had to recalculate the number. Too hasty. So it's 450 nanometers divided by 2 times 1.5. Well, so it's divided by 3. So equal to 150 nanometers. Good. So that's it. That's the, I guess, quick introduction to thin film interference. Sorry, this went longer than I had originally planned. Let me just wrap up thin film interference for, I guess, doesn't affect anyone here. This is summary of what we've been talking about. These are the new rules that you have to know or be reminded of. So the second example of air gap, it's so I don't need to introduce any more new rules. You can continue to apply this rule, just to pay attention to the situation you are looking at. So air gap between two glass plates, it might be like this. You have the bottom glass, and you have the top glass, so they're both glass. And maybe they are being kept separated by, I don't know, speck of dirt or something. That's keeping one end higher. So you are looking at some light coming in. So, the top glass, it would actually have some thickness. It's not, doesn't have to be infinitely thick. So here you have multiple reflections going on. But you could say, I think I can ignore all the other surfaces. The only two surfaces I'm paying attention to are these two surfaces that have air between them. And the beam path that I'm looking for looks like this. Beam comes in, reflects from here, and beam continues to go through and reflects from here. And I'm looking at how these two beams are interfering with each other. Good? And so we won't go through the detailed calculation, but this is what you will pay attention to as you are analyzing this. Index of refraction of glass, it's, I guess, 1.5, but what's important is that it's greater than 1, index of refraction in air. And the same thing here, index of refraction in this glass is greater than 1. So as you look at it, you go through the same considerations that you do before here. So you look at the point where beam 1 is reflecting. You look at the thickness that the beam 2 is going through, some kind of thickness. So you'll have to double it. It's air, index of refraction 1, so you don't have to change the wavelength here. And you would look at the reflection here. Okay? Now, on this top reflection here for beam 1, is there any phase shift? No, right? It's going from greater to smaller index of refraction. Okay, so beam 1, you get a phase shift of 0. So beam 2, it would get phase shift due to the additional length. So that would be 2 pi, now I'm remembering it, lambda over n. Oops, not lambda over n. The distance, 2t over lambda. Right? Now, but watch it out for beam 2. On this reflection, is there a phase shift? Yeah, it's going from smaller to larger index of refraction. So there's going to be a phase shift here. So plus pi. So it turns out, let me tell you a little bit of secret. If you ever get these two rules mixed up, you will never know it by the answers you get, because the answer will come out to be the same. What you have to remember is that the rules are the opposite for these two cases. I mean, this is the correct rule, but if you get them mixed up, turns out it's not as important as forgetting them altogether. Okay? So you have these two phases, you get the phase difference, and you would go through the rest of the calculation that way. And this is the demo you saw with this glass plate that was handed out. Your textbook actually has a picture of that there. Yeah, picture of that. When you have two glass plates that are placed very close together, then you get that kind of interference pattern. It's essentially showing a thickness that's varying on the order of tens of nanometers from the number that you saw calculated before. Because you vary the wavelength by 50 nanometers, it'll change which wavelength is getting destructively interfering and constructively interfering. The very last, I guess example 3, we don't really have to go over it. It's essentially the Newton's rings. It's a special case of this. It's air gap between two pieces of glass. It's that how the thickness varies. It's given by the geometry of the lens. So you guys can look at this, I guess, after you evaluate me. I have two lenses. I have only one, and I'm afraid it's going to get dropped, so I'm not going to pass it around. But I'll leave it up here. The obviously convex side, if you use that, you won't really see anything. Because as you saw, the numbers we are working with are super small. But it turns out, I realized that when I read your textbook more carefully, it has a picture of this. And the way they got this picture is by putting these two lenses, the plane, quote unquote, plane side together. The plane side is not perfectly plane. There's a slight variation of thickness about on this order. So when you put it on a surface and kind of look at the ceiling light reflecting from it, then you will see the alternation of bright and dark fringes. Combined with some rainbow color. So I'll leave this here. You can take a look at it after evaluating me or during the break. You have one more break before last period. So that's the thin film interference. So this is the setup of a Michelson interferometer, and it's quite unlike other interference setups that you have seen before. Because the other interference setups usually involve the things that are coming from more or less, or things that are occupying more or less the same physical space. When you had the double slit, the double slits are very close together. When we did the thin film interference, the path length difference you saw wasn't really that much. In this Michelson interferometer setup, the two beams that are interfering with each other, they, at some point in their journey, are separated by a large physical distance. And so this is a different setup. The basic consideration still remains the same in that you are looking at the phase difference between the two, and you can just set some particular reference phase, call that 0, and you look for phase change from that. That's the basic setup in any kind of interference analysis, and that doesn't change for the Michelson interferometer. But the arrangement here is quite unusual compared to what you have seen so far. And by the way, I want you to ignore this compensator plate. So we are going to assume that for our analysis, we have a super coherent laser that has a coherence length of infinity. Normally that's not the case, but we'll just assume that for now. So in this Michelson interferometer, what's done is you have a beam coming in. It's split into two parts. One that's reflected this way and travels this path, comes back, and then comes back here. And there's a beam that has gone, so this is a 50-50 mirror. So there's a beam that has passed through, and then it reflects off of this mirror, and then comes back, reflects here, and comes here. So you see that if I trace it out, the two beams, they share a common path at the very beginning and at the very end. So the parts that are different are the ones in the arms. So at the very beginning, here they share a common path, here they share a common path. So what you're looking at is the phase difference that takes place as these two beams are traveling in, wow, that blue path is way. Anyways, the phase difference that's taking place as the two beams are traveling these distances. And this is where it's important to think more in terms of reference phase, because these are macroscopic distances. You are never going to be set them in such a way that there's actually zero phase difference between them. So your starting place is you have them set up in a way that there's an integral multiple of 2 pi phase difference, and then you do something to one of these two arms that will cause that phase difference to change from that reference phase by a cycle or more. That's what you do observe, and that tells you something about something that you want to measure. Now, we are not going to do much with this interferometer setup, but the reason I'm bringing up this now is more or less for a historical reason. This interferometer setup plays an important role in the, plays an important role in the acceptance of special relativity that we are going to talk about in the next week. I want you to be careful because I didn't want to say development, because I'll talk about this next week. So I want you to be aware of this interferometer setup because it's important to history of physics. But as far as your exam is concerned, I probably won't give you any exam questions that pertain to this. So what I want to do now is you can actually, if you have the correct lab apparatus, which we don't, you can actually use this to measure index of refraction of air. Do people remember index of refraction of air? Very close to 1, but it's not exactly 1, right? So how close to 1? There's some number of zeros. I want to say it's 3 zeros and then 1. I'm not actually sure. Let's look it up. Index of refraction of air. So it's very close to 1. What I'm not sure is how many zeros. Okay, it's 3 zeros, and then, okay, not 1, but 3. All right, so that's the index of refraction of air. You guys remember the reflection and refraction lab, right? Yes? Using the methods you use it in the lab, can you imagine measuring this? Index of refraction of anything with, I guess, 3 parts in 10,000? No, none of the methods that you use there is that precise. Interference is. You can use Michelson Interferometer setup to measure index of refraction of air with the setups that are like in an instructional lab. I'm not talking about setup that's available at national labs. So the thing that we don't have is I don't have any, so this is the setup for measuring index of refraction of air. So this is the schematic diagram of the setup. And what I'm telling you that I don't have is I don't have this. I have to have this built somewhere to be able to do this lab. But that's really the only thing I don't have. If we had a chamber that we can vacuum out, then we could actually measure the index of refraction ourselves. So what I want to do in about, hopefully no more than 10, 15 minutes today in class is just to do a quick calculation that would at least give you some sense of what we would need to measure to be able to actually measure index of refraction of something with this much precision. Okay? So let's use this setup here. This diagram makes sense to everyone, what it's representing? Yes? Good? Okay. So because we don't have an actual physical setup that I can show you, what you have to imagine that you are seeing here, or don't put your eye in the path of the laser beam. What you imagine placing a screen here and observing from over here is you are going to imagine seeing this pattern of interference. So in the very middle of the circle is where the two beams are destructively interfering. So somehow the path length difference works out so that you have a half a cycle difference plus however many integers. And as you move out by geometry, by some difference in angles, as you move out a little bit, constructive interference, back to destructive, back to constructive, destructive, and so on. And what you would see is as you change one of those two arms that you saw, as you change the, let's say, amount of air in this arm, you are going to see this interference pattern shift. So it'll look like these circles kind of moving outward. So there will be a bright spot that happens in the middle. So bright spot that happens in the middle, and then as you pump out more air, then that bright spot will turn into dark spot again. So that's what you are noticing as one full cycle of that indicates that the phase of the light beam that's gone through that other arm changed by one full cycle. Everyone has that correct image in your head? Like if you were doing this lab, you would know what to look for? Kinda? Okay, yeah, okay. So that's what I want you to imagine. So what I want to do is I just want to work out some numbers. How should I do it? Let's use the numbers that are given here. So it gives the size of the chamber that could be vacuumed out. So let's go through a series of questions. So does the wavelength of light matter here? Like what we are going to do calculation of is we are going to look for, as we are observing here, what we are going to look for is number of cycles of fringes shifted. That's what we are going to look for in this screen here. And we have a number fixed here, length of the glass chamber, or path length here, or physical length there. So I just want to specify any other numbers that we need to specify. The wavelength of laser, is that an important part? Is that a parameter that matters numerically? Yes, no? I hear a lot of no's and I don't see any yes. Anybody say yes? Why does it matter, Crystal? Your intuition says yes. It's a good intuition. So if you want to be more specific, this is what it is. In the end, what we care about is phase. Phase is what we care about in the end. We don't care about physical distance. We only care about phase. And you could specify it as cycles or specify it as radians. So what matters here is, so you are given this physical length, and you need some parameter to turn this physical length into something that can be compared to a phase. So what would you need to do that? Wavelength, right? Because you have some distance, and wavelength tells you how much distance is in one cycle. So if you have some distance, you want to turn it into some number of cycles, you need a wavelength. So here, maybe it's possible that it could cancel out, but let me just assume that wavelength is going to matter, because I know that I need a wavelength to turn this into number of cycles. So wavelength, let's say it's a helium neon laser, 633 nanometers. So that's a reasonable number. Let's go through some other parameters that I think won't matter. This distance here, will it matter? No, because it's common to both beams, right? No phase change here. What about this distance? No. Doesn't matter for the same reason. Now, what about this distance? Does that matter? Yeah. Now, if you're looking for absolute phase difference, then sure, yes, it matters. This is why it's important that you know what you're looking for. So you are not, this is the distinction I want you to draw. You are not trying to predict, is the center going to be dark or bright? You're not trying to do that. You take this as it comes out. Maybe the center will come out to be dark. Maybe it'll come out to be bright. And after you have that setup, all you are going to look for is the change of one cycle, or change in the number of cycles from dark to bright, back to dark. So if you're trying to predict, is the center going to be dark or bright, then yes, in that case, yes, this length would matter. But since you're just going to take whatever pattern that appears here as given, whatever this length is, Actually doesn't matter for us. Good? That argument is convincing to everyone? And can you say that the same for here? Whatever actual length is here, it doesn't actually matter. Right? Okay. So the only thing that matters is the change that's going on here. So when you initially place this glass chamber, you'll get some kind of interference pattern here, and you are changing just the one thing. You are changing the index of refraction in this chamber. It's going to go from initial index of refraction of this value, 1.0003, to it's going to go to some final value of 1 if we vacuum it out completely. Okay? So that's going to lead to some amount of phase difference from the reference phase we had. And that's going to turn into the number of cycles of fringe that you will see. So let's just take a quick estimate in the number of the cycles of fringe shifted and see if that's something that one could expect to reasonably measure. Good? All right, so let me start out with a phase shift. Just change in phase from glass chamber being vacuumed. I'm being a little bit specific here. I'm not looking for phase difference between the two arms. Whatever the number is, I don't think I'm going to be able to predict it. I'm looking for phase change, not difference. Okay? So I want to look at it this way. I want to count the number of cycles I had here initially. So let me call this number. So I'm actually just coming up with a formula on the spot based on my physical intuition. There's no pre-made formula that I can look up. I'm just thinking, all right, I have that physical distance. I want let me write down the general outline of this formula. So for this phase difference, this is what it's going to be. It's going to be 2 pi times initial number of cycles minus the, final number of cycles minus the initial number of cycles. So final number of cycles minus initial number of cycles within that glass chamber. Like, does this expression make sense? Like, the first time you see it, you might not guess it, but once it's been spelled out, I'm asking, does this make sense? That's what we are looking for. Okay, good. So now what I'm going to do is I'm going to write out an expression for final number of cycles based on the parameters we decided. Same thing for the initial number of cycles. Get a difference, get an expression that way. This is the kind of thing you would do when you are working in a lab. A lot of the things you do, you don't have a pre-made formula given to you, but many things are things that you can figure out as you go because it's, once you know the underlying theory, it's intuitive. It just depends on some simple arrangement of things. So final number of cycles, that would be, so I want to propose this as the general formula for number of cycles. See if it makes sense. Number of cycles within a given length is equal to given length divided by the wavelength in the medium. So wavelength in vacuum divided by n. That's the number of cycles in a physical path distance of d. Right? That's what we've been using for thin film and other stuff, right? It doesn't change it here, so all right. So I'm just going to use this. So between these two, D hopefully won't change. It's the same glass chamber. Hopefully it's not contracting or expanding in size. So the only thing that will change is N. The wavelength in vacuum, that's just property of the light, so that won't change. So this phase difference is 2 pi times final number of cycles. Let me simplify this a little bit. This is N times D over lambda vacuum. So it's the final index of refraction, which is 1. So d over wavelength in vacuum minus the initial number of cycles. I should have had them flipped. Doesn't matter. I'm going to get a negative answer, but I'm only looking for absolute value anyway. So it's going to be, so this n initial is the index of refraction of air. So index of refraction of air times the distance over the lambda vacuum. So this is the expression. And once you get that, you can simplify this a little bit more. So let me do that. It's 2 pi times d over wavelength in vacuum. And it's 1 minus n air. Let me write it out differently. So minus the index of refraction of air minus 1. Good? So this is actually one of the source of the high precision in interference measurement. When you do interference, you are essentially making a difference measurement. If we were imagining measuring this as from 0, then what you need is a precision of 3 parts in 10,000. But instead of that, imagine you are measuring n minus 1. Then you're still measuring a small number. You're still measuring 0.0003. But you don't need a high precision on that measurement itself. If you had, I don't know, 10% error on that, then instead of measuring 0.0003, you measure 0.00033. Okay? So for those of you who go into fundamental physics research, this is in the area called precision measurements. And a lot of precision measurements are based on interference for this reason, because in an interference measurement, you are taking a difference between two very large numbers. And that difference can be taken very precisely. Anyways, let me finish the calculation here. So I'll just plug in the numbers. So that'll give me the phase. Actually, let me plug in this number. Instead of plugging the numbers right now, if I take this and divide out the 1 over 2 pi, this is going to be the number of cycles that I should be looking for anyway, right? So I'm going to ignore this 2 pi, calculate d over the wavelength, and that times 0.0003 will give how many fringes I should expect to see. Okay? So let me plug in those numbers. So d is 2 centimeters, or 2 times 10 to the minus 2 meters. Lambda is 633 nanometers, or I'm just going to use approximate numbers, about 600 times 10 to minus 9 meters. And the index of refraction of air minus 1 is going to be this, or 3 times 10 to minus 4. These are numbers I can do by hand. So 10 to, let me do this in different color. So it's 10 to minus 6 divided by, this is actually 6 times 10 to minus 7. So 2 divided by 6, so 1/3, times 3, so 1. So working it all out, this should be, so 2 divided by 6 times 3 is 1 times 10 to minus 6 divided by 10 to minus 7 is, people here can do powers of 10 calculation in their head? 10, right? Yeah, 10. So the number of cycles you will see is 10. Do you think you can count to 10? Right? And if you're counting 10 cycles, your precision will be at least 10% on the number of cycles you're counting, right? What that means is your precision on the difference will be 10%, which actually translates to something like 0.01% error on the final answer. or 0.01, yeah, something like 0.01, 0.03% error. So, so this is the kind of measurement that you could actually do in an undergraduate lab with a very modest instrument. And what we'll describe later on, I guess next week, is the kind of experiment that Michelson, whom the interferometer is named after, Michelson and Morley did. They were trying to measure the variation in speed of light. And this is one of the most famous null result experiment where they measured zero. They didn't get anything. They were looking for variation of speed of light. They measured zero variation of speed of light. And because, but even though it was null result, because their setup was so precise, they could set very high constraint on how much the speed of light could vary. And this was an important factor in people accepting what we today call Einstein's special theory of relativity.